So, Blutsanger. It's a very German term. Yeah, because it's German for blood singer. I'm going to go into why later on, but closed loop perfusion with artificial oxygen carriers. It sounds like a heavy metal band, and there's a good reason for that. So, what is Blutsanger? Now, kind of the introduction, summary. This is going to be a brief one. I'm not going to go into full details because there's still some active research and intellectual property involved in this particular project. But overall, the problem is cardiopulmonary deaths are responsible for a third of deaths worldwide, and COVID, of course, being a high-profile example of that recently. And in the US, over 400,000 patients died of lack of transplants and lung disease. And common life support techniques like veno-arterial extracorporeal membrane oxygenation has about 50% patient mortality. And the 40% of the survivors have lasting brain damage because of complications from the surgery. So not a good thing to go on life support. Artificial hearts have existed since the 70s with Robert Jarvik, the guy you see there with the Jarvik 7, but artificial lung technologies really lag. So overall, background is oxygen-carrying nanoparticles have been in medicine since the 1980s, especially fluorofluorocarbons. People have tried making artificial blood for a variety of reasons, like military medicine, to keep divers underwater for longer during the Cold War, and a lot of other reasons. But fluorofluorocarbons can carry oxygen through the body and replace it for CO2. They're not viable as a full blood replacement, but they're great as a supplement, like a way to carry oxygen around. They're still used today in various niche cases, like keeping transplanted organs alive or helping patients who are at risk of ischemic injury. Now, one thing you're thinking of is what's called acoustic tweezers. Essentially, it's using focused ultrasounds, like the transducers there, to separate out the nanoparticles from a flowing medium. So the acoustofluidic tweezers to separate out the fluorofluorocarbons is kind of the basis of the idea here. Now, acoustic tweezers have been used in industry for years, but for the most part, focusing on this particular application, all right? So in addition to VA ECMO, there's artificial lung companies that have come at it with different approaches. One of the main parallel engineering approaches is Dr. Potke's lab, former University of Michigan professor. His is basically trying to mimic how the lung works using bio-inspired polymers, expensive plastics that mimic fibers in the lung. But the problem is blood clots form because they're not natural materials. So it's only viable maybe for a week at best, even with like a blood clear of antibodies. And the flow rate cannot match that of a natural lung because the fibers wear out much faster. So you can't support the 5 liters per minute that a normal adult patient would need. So the Blutsanger is an attempt at a closed loop acoustofluidic blood separation system. Oxygen-carrying nanoparticles, the fluorofluorocarbons, are injected into the blood and retrieved with ultrasound separation when expended. We reoxygenate them, we remove the CO2, and we re-inject them into the peripheral arteries and veins. So essentially, we can use arms and legs instead of the neck like ECMO does. So it's more like dialysis, respiratory dialysis, than necessarily conventional heart and lung machine. The device can be combined with a vascular assisted device, artificial heart, or heart pump for both acute, that is emergency care, or chronic, like a transplant or bridges transplant or transplant replacement case. So the implementation was we had an Italian company make a acoustofluidic cell. We sent it to a university in Germany, to Duisburg-Essen, who made the nanocapsules. We still needed to optimize the MEMS system, the acoustofluidic stuff, because we need the right resonant frequency for the nanocapsules to overcome the drag motion in the flow. Because the nanoparticles are not separating, for now at least, so we need to do a lot of brute force combinations of frequency and power to find the one that will work, because people have separated bigger and smaller nanoparticles, and that's always the trick to it. So the goal is to build this as an acoustofluidic system. We're trying to use this later on for a 3D bioreactor to culture neural cells and mimic the brain. It requires expertise in artificial oxygen carriers, MEMS, microfluidics, and securing funding. So, yeah. Here is the references right here. Thank you very much.
Thank you very much.